Hello everyone, my name is Varun Lautka and welcome to my Capstone project presentation. Today I'll be walking you through my project that is called Multi-Nutritional Deficiencies Diagnosis Using Lifestyle and Clinical Data. In simple terms, I build a machine learning powered screening tool that can look at patients' demographics, their lifestyle habits, their physical symptoms, and their lab results and predict whether they might be suffering from a specific vitamin or mineral deficiencies. This is a machine learning powered clinical screening tool designed for early detection, catching problems before they become serious. So let's start. So, why do we even need an AI tool for this? Let me give you a few numbers that set the stage. Roughly 1 in 3 Americans are deficient in at least one vitamin. That's staggering, right? About 50% of those deficiencies go completely undiagnosed until the person becomes visibly symptom, by which point the real damage may already be done. So over $30 billion a year in the US alone gets towards treating nutritional related illnesses that could have been caught earlier. Now, the clinical challenges here are real. Symptoms of uh, vitamin deficiencies are often non-specific. For example, fatigueness could mean iron deficiencies, B12, or just a bad night's sleep. Lab tests are expensive and time consuming, so doctor don't always order them unless they are a clear red flag. Clinicals may not proactively screening patients without obviously risk factor, and on top of all that, rural and low income population people are at most risk are the ones which the least access to this test. So our solution is an AI powered screening tool that takes in patients demograph, lifestyle factor, physical symptoms and lab tests and flag potential deficiencies early before the irreversible damage occurs. Think of it as a first class filter that says, hey, the patient's profile look like it could be consistent with vitamin D deficiencies, or maybe order the uh, blood panel. So data and methodology. uh, Let me walk you through the dataset and how we prepare it for modeling. We work with 4,000 synthetic patient records, and I want to be upfront about that. This is synthetic data, it's not pulled from a hospital. It was designed to mimic a realistic clinical distribution. Each record has 33 input features, and the models predict across 9 disease classes, 8 specific deficiency plus, plus a healthy category. The dataset is balanced, meaning each class has roughly equal representation, which is really important for training a fair classifier. The features fall into four groups. First, demograph, age, that is age, gender, BMI, income level, and latitude region, because we live affect our skin exposure, which affect your vitamin D level. Second, lifestyle factor like diet type, whether the patient is vegetarian or vegan or eat a balanced diet, their smoking status, alcohol consumption, and exercise level, as well as the sun exposure. Third symptom, we have 8 binary symptom flag like night blindness, fatigue, bleeding gum, bone pain, muscle weakness, and so on, along with the total symptom counts and a multi deficiency flag. And finally, lab marks, percent RDA values for 8 different vitamins plus hemoglobin serum, vitamin D, serum B12, and serum fluid. For this machine learning pipeline, we started with data cleaning using model imputation for our missing values. Then we applied one hot encoding for all categorical variable, standardizing everything with a standard scalar, and use a 70-50-50 standard training validation test split. Coming to the diagnosis score. So there are the 9 conditions our model can detect. The first class is simple healthy, no deficiency detected. Then we have vitamin A deficiencies, which presents as night blindness, dry skin, and weakened immune function. Vitamin C deficiency, which most people know is scurvy, bleeding gums, fatigue, poor wound healing. Vitamin D deficiencies, this is the one very common and lead to tickets and children. uh, Osteomachia, I don't know how I pronounce it, but uh, yeah, that causes bone pain and muscle weakness. For vitamin B12 deficiency causes numbness, tingling, memory loss, pale skin, and anemia. Folate deficiency can lead to metabolic anemia and poses neurodevelopment risk, especially during pregnancy. Iron deficiency is the most common nutritional deficiency worldwide. Anemia, fatigue, pale skin, calcium deficiencies are hypokalemia, muscle cramp, brittle bone, and finally vitamin E deficiency, which is less common but causes nerve damage, immune dysfunction, and vision problem. So this is a genuine multi-class classification problem with a clinical meaningful outcome. Coming to the next part, exploratory data analysis. Before building the models, I conducted a thorough exploratory data analysis. This slide converts the two key findings. First, the target class distribution. As you can see the bar chart on the right, the 4,000 records are distributed fairly equally across the 5 main health categories. This is critical because a balanced dataset prevents the model from developing a bias towards the majority healthy class and ignoring the rare condition. This is exactly why our model can successfully identify condition-less curvy and high precision, even though in a real world populations curvy could be far less common than say like iron deficiency. Second, we took a lifestyle um, versus biomarks. As you can see the top 10 clinical and lifestyle breakthrough chart, it provides clinical validation that lifestyle factors like diet type and sun exposure directly correlate with blood uh, markers like vitamin B12 and vitamin D levels. I think this is important because it tells us that the patient history alone can serve as a strong non-invincible signal for internal health. This clear expectation of median value across these features also validates the quality of our synthetic data. The pattern it contains are medically sensible. Coming to the next slide. This slide dives into the feature correlation matrix. What you are seeing is the big correlation map across all patient vitals and demographic features. The key takeaway here is the identification of our top drivers, that is serum, iron, vitamin D levels, and hemoglobin emerge as the most influential diagnostic features. And what's really encouraging is that these are exactly the features the real world clinical relies on for nutritional assessment. So the AI mathematically priorities align with actual medical diagnosis standard. for a dimensionally standpoint, while we fit the model 33 features. This analysis shows that a clinical drive of iron, vitamin E, and B12 carries the most predictive weight. The strong rate diagonal conforms each feature correlates with itself, and the top diagonal patterns reveal meaningful cross-function relationship the model can exploit. Coming to the model selection. So I train across 4 different classifiers, starting with logistic regression as our baseline. It's fast and interpretable, but with an accuracy of just 66% and recall of 66%. It struggled with the multi-class nature of the problem. Its linear decision boundaries simply couldn't capture the complex features interacting we needed. Coming to the support vector machine, it did better with 71% accuracy and similar recall, but it's slow to scale and still fell short. XGBoost was a big jump forward with 91.5% accuracy and matching recall. It's powerful gradient boosting method and it performs impressively. Uh, but Random Forest was at 92.4% accuracy and 92% recall, and we didn't pick it. Sorry, and we didn't pick it because it was the highest score. But the per class table where it gets interesting. Uh, the model excels at identifying healthy patients with 96%. So there are like 4 specific reasons it achieved the highest recall on minority classes uh, like ricklets and scurvy, which are the condition we most needed to catch. It naturally handles mixed feature type without additional encoding headaches. It's resistant to overlift thanks to the assembled wording across hundreds of decision trees, and its output probably estimates, which means we can eventually build confidence scoring into this application. So random forest was our selected model. So model performance, let me break down how well the random forest perform on our held out test. At the top level, 92.4% overall accuracy with 91.8% Marco recall and 91.6% Marco F1 score and 92% those are the strong number across the board. But the per class table is where it gets really interesting. The model excel at identifying healthy patients, 96% precision, 97% recall. That's important because you didn't want a false alarm. Vitamin D deficiency is the most common condition. Is detected at 93 to 94%. Iron deficiency and vitamin B12 deficiencies are both in 90 to 92% range. Where it gets harder is the vitamin C and vitamin E deficiency, down to 83 to 85% range, and this marks clinical sense. Vitamin E deficiency has the fewest distinctive symptoms, so there's less signal for the model to pick up on. And a few key findings worth calling out. The stratified training test split was essential to prevent class imbalance bias, and the balanced dataset roughly bought 142 records per class. It is what made this minority class recall number possible. coming to the application. So all of this model wouldn't work for the academics if nobody could actually use it. That's where the Streamlit web application comes in. I built a clean three column interface. On the left, you have a demographic panel where user enter age, BMI, gender, income level, and altitude region. On the middle, lifestyle panel covering diet type, smoking, alcohol, exercise, and sun exposure. On the right, a symptoms checklist with 8 binary flags. The user can toggle things like fatigue, bone pain, or bleeding gums. Below this, there is a lab result section with a slider for the RDA percent for each vitamin and numerical inputs for serum level and hemoglobin. On one click on analyze button and the app constructs a data frame, applies the exact same one hot encoding and standard scalar processing pipeline that we use during training. It aligns the feature column to match what the model predicts and returns a diagnosis within second. If the prediction is healthy, the users get a green successful message. If a deficiency is detected, they get an orange warning with a recommendation to consult a healthcare provider. Um, the entire app is developable to Streamlit Community Cloud with zero interaction and management needed. The link is right over here, you can check it out. Coming to the current limitation, so no project is complete without an honest look at its limitation, and I want to be transparent about the six specific. But first, this model was trained on synthetic data performing on real clinical population is invalidable. Second, the feature scope is limited. We are missing cometry, active decision, and genetic mutation factors that real clinical relies on. Third, symptoms are binary, just present or absent. Real clinical assessment captures severity, which add importance to it. Fourth, this is a static model. There is no online learning. If new data comes in, we have to fully retain. Fifth, we can only predict a single level per patient. If a reality patient often suffers from multiple simultaneous deficiencies. And sixth, there is no explanatory layer. The model gives you a label, but you don't. But it didn't tell which symptoms you are lacking. This is why a real trust barrier when you are asking clinical to act on it. But all of these are solvable problems, and they lead directly to our future work. So even with this limitation, this tool has meaningful real world application. Let me walk through 6 of them. In primary care clinics, physician could use this for pre-visit screening, flagging at-risk patients before ordering expensive lab panels. This one could reduce unnecessary costs significantly. In rural and unserved communities where lab access is limited, this app works on any device with a browser and requires no physical lab requirement. There's a patient interview and some basic biometrics. So for medical education, students can uh, reside and can use it as an alternative case study simulator, learning how different symptoms and lab combinations map to specific deficiencies. And at the public health level, uh, it could help agencies identify nutritional deficiencies hotspot by uh, geography or demographic. This could directly support policy decisions. It could also integrate as an backend API into customers' supplement and nutritional app for personalized dietary recommendation. And finally, employers could offer anonymous vitamin deficiency screening through workplace wellness program. Coming to the future work. So I've organized the roadmap into three phases. Phase 1. In the near term, 0 to 6 months, the top priority is partnering with a clinical or hospital to get early identified EHR data so we can retrain our uh, validate the model and with real patients. Alongside that, we'll add sharp SH help and adaptive explanations to give uh, clinical a clear breakdown of which features drove each prediction. Explainability is non-negotiable for patients' trust. Phase 2, middle term, 6 to 8 months. Uh, we have we will redesign the output layer to support multi-label prediction because real patients can have more than one deficiencies at a time, and will replace the binary symptom flag with 1 to 5 severity scale for finer grained risk for filtration. Phase 3, long term, 18 months and maybe beyond. Cross platform mobile app for iOS and Android, purpose built for point of care use in rural clinics, and a continuous learning pipeline so the model update incredibly at a new validate patients data flows in, and no more full retraining every time. The overall vision is clear: clinical, validated, uh, explainably multi-label vitamin deficiency AI, accessible to any patients anywhere on any device. To conclude everything, let me wrap up with the five key takeaways. First, our random forest model achieved 92.4% accuracy, outperforming logistic regression, SVM, and XGBoost on the dataset. Second, the system analyzed 33 features across 9 diagnosis classes. That's comprehensive input score that's enabled genuinely for multi-class diagnosis. Third, the Streamlit interface is clinical ready, designed so that